কোথায়? Oh, I see. Oh, that's not being seen there. Oh, that was off. Okay. So, in the last class, we have seen how a single purpose processor can be designed. And a single purpose processor is also known as an ASIC, application specific IC. Now, the example that we have given in the last class was for computing the GCD of two numbers, two integers. Now, that is an example of data dominated computation. On the other hand, if I give an example of another task, that suppose I am to design a system that will accept timer signals, I mean some events, I would say some events which are coming at specific time, and whenever, say this event is coming every, let me put another one here, this event is coming every 10 millisecond, right, every 10 millisecond this event is coming, and whenever this event comes, this system should read a temperature. Temperature which comes at as 8 bits. Okay. That is being read through some port. We will need some port, of course, that is a design issue, and two thresholds will be fed, threshold 1 and threshold 2. If temperature is greater than threshold 1, then start coolant or start fan. So, some fan should be actuated for cooling it down. If temperature is less than threshold 2, then start heater. All right. Now, this is the requirement. Just look at this and tell me if there is any gap. Let me also check whether there is any gap, because that is very important. Whenever you are giving the specification, that is very important, whether there is any miscommunication or there are some gaps. Events are coming every 10 millisecond. So, at every 10 millisecond, I have to sense the temperature. All right, that I have not written over here. On event sense temperature, let me write down. On event read temperature. All right, and then it is being compared with this. Now, this one you will have to design. So, I am right now today I am leaving it as an assignment. We will work it out at a later date. Okay, but for everybody, I would want that you try your hand in designing this very simple system. Okay, you will have to design its control path, and data path. In continuation of what we were discussing in the last class, you will discover when you design it that here the data path will be much simpler than the one that was with GCD, whereas the control path will not be very simple, but not very complicated here also. It is a very simple problem, but I want that you try it out. Okay. So, this is one of the assignments, and we will come back to this maybe after a couple of weeks to redesign this. Okay. And now, today we will discuss about some optimization issues. I will initially go back to the earlier design that we had done. We had designed this data path and control path for the GCD, right. We had 2 registers to hold the values, the control lines, the 2 multiplexers and 4 operators, and ultimately we got the GCD, and there were 10 states. Now, when we carry out the optimization of these, that means there is the scope of managing or reducing some redundancies that are already there. Now, the redundancies can be there. We can do the optimization in the original program itself. We can try to optimize the FSMD, we can optimize the data path, or we can also optimize the controller, okay, the complexity of the controller. Each of them we can do. Now, optimizing the original program. Just if you think of a little bit, looking at this program that has been given for computation of GCD, can you see any scope of computing less or making it more efficient? If you work out this part, you will see that I am repeatedly comparing and subtracting. I am doing that repeatedly, whereas the typical GCD that we compute, say 225 and maybe 25, I am trying to divide this 9 times, right. So, then this becomes straightway, it is coming as the GCD. So, I am not say again, let us say 15 and 200. If I do, what do? I repeatedly divide, right. So, and I take the remainder and then divide and go on dividing till my remainder becomes 0. So, I can continuously check for the remainder to be 0. If not, I will take the remainder and repeat the division with that. That will save me from repeated subtraction and repeated comparison of P and Q. So, if I try to do that, you see this part compared to what I was drawing on this green paper and the one that has been given in the slides of Weiss and Gevarghis, my P and Q are his X and Y, all right. So, please bear with me to make that replacement. So, here you see in the original one this was the loop, while x is not equal to y, if x is less than y I subtract, else I do the other subtraction, and this thing I do. Now, if I replace it here, while y is the remainder or the while y is not equal to 0, say like this what is the numbers that I have just now taken, 15 and 200. So, 15 is the y, while y is not equal to 0, I am taking the modulus, r is the modulus, and modulus means the remainder. So, say 200 divided by modulus integer division 15. So, that is leaving me with the remainder 3. Then I am just doing x, y is now being assigned to x and r. So, they are being changed, y and r, they are being just swapped here, and I am repeating this. So, now look at, compare this, how many operations I had to do here. There was a comparison operation, there was a checking operation, that checking operation is nevertheless here. There are 2 subtractions, and here there are assignments, 2 subtractions and 2 assignments, right. Here I can just do simple 2 assignments and 1 operation of modulus. Thereby, the entire program has been made more efficient. That will save in the number of clock cycles also, the number of that I need. Here, I need to say if I take 42 and 8, if you work it out, it will take 9 iterations to complete the loop. 42 divided by 8, that is being done, it is not being done by division, it is being subtracted, 42 minus 8, right, 34, and in that way it goes on. So, it takes 9 iterations, whereas if I do it in this algorithm with these operations, then I can get it done within 3 iterations. So, this is a very nice example of showing how I can play with the algorithm itself to go for a more computationally efficient algorithm. The next stage is we can optimize the FSMD itself. There are, because you see when I had drawn this FSMD, this is the same as we will see, just drawn in a different way. I did not bother about minimizing the states, whether anything useful is being done in between in the states or in between the states. I did not bother about that. I simply translated this algorithm into this diagram step by step. Now, it is time that I can have a deeper look at this and see if I can reduce this. Okay? That is the second step. So, we can say here, now this state is actually not required, right. Now, we can simply merge these 1 and 2 or eliminate this 1 and start with 2. Okay. And in 2 and 2j we have here what is being done, 2 is on, not go, I am going here and again coming back. So, that could be very well done with a self loop, right. So, 2 and 2j can be merged to give one state 2, right. So, on go I come here and on not go I remain in the loop. Next, 3 and 4. These were 2 distinct steps in my algorithm, and accordingly I had kept them as computational states. right, as computational states. Now, I can straightway merge these two. I can merge these two, and in one state I can do two computations. Why? Why? Because these two computations are completely independent. They are in no way dependent on each other. I am taking from one source and loading in one register, taking from another source and loading in another register. So, I can merge these two and I get one state. Next, 5 and 6. Similarly, the assignments operator is independent. Now, this transition from 6, I can very well take it from 5. There is no need of x not equal to y, I come to this and then take a transition. I can also merge these two, and so my scenario becomes this. But you see here, 7 and 8 cannot be merged, there is no question of merging. These are two alternate paths. I can take any one of them, all right. I can take any one of them depending on the two different conditions, right. So, these two are kept as it is. This is for x less than y and this is for x not less than y. And then I loop. Now, these things that were there, 6j and 5j were there, they can also be, the transitions. Here what I was doing, from 7 I am coming to 6, from 8 I was also coming to 6j, and accordingly I was doing the transition, but that is how it was written in the algorithm, but I can straightway merge them and come to this point. Therefore, this becomes a reduced state diagram. So, how many states did I have? 9 states or 10 states. Here I have got 1, 2, 3, 4, 5, 6 states. 6 states, how many flip flops should I need? 3. 3 bits. How many bits do I need? 3 bits. And earlier I needed 4 bits. Why? Where did I need those bits? For encoding the states. Now, here since the number of states are less, the number of bits required is also, since there are 6 states, I can do that with 3 bits. So, I will be needing 3 flip flops, thereby I am optimizing. Not yet coming to the complexity of the control path, but purely on the number of flip flops. Okay. So, that is the second part of optimization that we can do. Optimizing the data path, that was a little evident in the last class itself. What we did is one-to-one mapping that we did. You can come to any one of those diagrams. Say for example, this diagram where I needed P and Q. I had put in 2 subtractors and everything, and there was one-to-one mapping. One operation with this subtractor, one operation with this subtractor. But I can very well reuse the subtractor, because why? Why can I reuse the subtractor? Both of them are not being used at the same time. Therefore, I can use the same functional unit, right. Also, I had used comparator. There was one not equal to, there were 2 subtractors. If I had, but now if I look at this algorithm, let's here. So, except for this, which I can merge in one state, this is purely loading. This is no arithmetic operation. This assignment is purely the task of loading the controlling the multiplexer and loading the registers. So, that is not an issue. Here, none of these operations are being done concurrently, right. So, I can very well, I could have used one ALU for that. Now, I have to see whether the cost of the ALU is more than having them separately. A simple solution is, of course, the subtractor could be reused, or I can see if I can use the ALU also. But you see, can you, if you just think a little bit, as soon as I use an ALU with this, here I am using separate things, right? And accordingly separate control signals will come to each of them, activate them. Now, if it be an ALU, there will be different control signals coming. So, the control circuitry will also be changed. So, the optimization criteria are multifunctional units or sharing of the units. And the other thing is the optimizing the FSM, the state encoding. We can assign a unique bit pattern to each state. Size of the state register and the combination logics vary. We can minimize the states, multiple states into a single state, that is possible. Okay. So, in these different ways we can carry out the optimization. So, summarizing what we have done in this design.
State encoding is not an optimization, right? State encoding we have to do.
State encoding you have to do, but there are ways and means of encoding by which you can reduce the number of, reduce the complexity. See that. So, because here the way you assign the unique bit pattern to each state, that is very important, because accordingly you will have to use the flip flops also. All right. Now, so what we have done in this exercise is we wanted to design a GCD as a simple example. Okay. We started with an algorithm, fine, and we translated that algorithm into the control data flow graph or FSMD, which we got here, not here. Where is that? We got an FSMD here, right? And based on that, looking at that, we developed the data path, and then we first developed the data path, and then we proceeded to design the control path. Now, after we did that, we went for optimization. Now, there are EDA tools, there are tools, electronic design automation tools, these are also known as EDA tools, which allow you to describe the behavior of a circuit in a or behavior that you want to do using some standard languages, specification through some standard languages. We will learn some languages, but very common are VHDL, Verilog, etc. There are other languages, we will look at them as state chart, SDL, so on and so forth, we will look at those. Now, this specification is fed to a design compiler. This specification is validated, and then you can call it a design compiler. That leads to the data path and the control path, and optimizations are done. So, for complicated circuits, we will not be able to handle all the optimizations manually, but after that, after the optimizations are done, then this thing is brought in to the actual implementation, followed by testing. Okay. That is more or less the flow of the tools, the EDA tools. Now, So, now summarizing whatever we have discussed up to now, that is, for embedded system design, we can utilize general purpose processors, we can utilize ASIPs, or we can design single purpose processors. Single purpose processors, right? Now, if we look at it from the flexibility side, then as we move in this direction, we are gaining more and more flexibility, right? If we, but obviously, if I just put another axis of NRE cost, I mean the time to market, time to design, which way does it increase? It will increase in this side, right? Now, as regards speed, which side should be faster? This side should be usually faster, because here we are getting everything on dedicated systems. Here there is software components involved, which are being interpreted by the processor, and that is a relatively slow than this. However, the NRE cost or the time to market will increase if I want to make single purpose processor for everything. So, in between these two, in between this range, there has been another segment which is known as programmable devices, programmable logic devices, or PLDs as they are called. And ultimately, in embedded system market, a variant of these PLDs, a much more advanced version of them, has come in the form of field programmable gate arrays, right? Field programmable gate arrays. In short, they are known as FPGAs. Okay. These FPGAs are hardware, but their interlinks can be programmed. All right. Interconnects can be programmed, and that can be done using some software, and once that interconnect programming is pumped into the FPGA board, then that particular FPGA can carry out any logic function of your intention. This is one step. What typically we do is, if I have got an idea of a design, we may like to do it on an FPGA quickly and see whether my functionality is met. Only then, and sometimes that FPGA solution works fine, all right. It will be a little slower maybe than the this thing, but it's much more, it's not as flexible as these, but there are certain advantages of this which I am coming to again. All right, not as flexible as the general purpose processors, but it is much easier to program. I can reprogram them if I like, depending on the type of FPGAs. Okay. So, an FPGA or FPGA is essentially a scenario like this. We will have an FPGA board on which there will be several I/O pins. On all sides. With which we can connect to the external world. And there are a number of CLBs. This is CLB. What is CLB? CLB stands for configurable logic block. These are configurable logic blocks. There will be an array of these. Typically, the present day FPGAs give you around 300,000 such CLBs on the typical chip, on a typical FPGA chip. The FPGAs, the best known FPGA manufacturers are Xilinx, did I spell it correct? Or Actel. And there are others also, I shouldn't say, but these are very popular. Now, there are a number of combination logic blocks, and these are surrounded by a number of interconnection wires. Huge number of interconnection wires. Now, these interconnections I can very well program. All right. Now, this, so I can, just to give you an idea of how this is, what do I mean by this programmability? Let us go back from FPGAs to their earlier predecessors, PLAs. Okay, I mean, there's where imagine you have got an array of AND gates. There are some interconnections. This is an AND plane where there are number of AND gates, and there is an OR plane. This is the OR plane, and here is the AND plane. Okay. So, here at this level, green level, are the colors visible? Yes. Suppose there are a number of AND gates, right. And on this side, there are a number of OR gates. recall that any logic function we can write as say x y, or we can write as a combination of and or as the mean terms, right. I can write in this way. Three input, say I am talking of a 3 input function x, y and z. Suppose this. Now, this is nothing but a combination of ands and ors. Therefore, it is possible for me to implement these functions if x, y, z are available here, then I can connect, if I can connect say this AND gate, and here I put in x and y, and I connect this and connect this to this OR gate. I take y here, this is x, this is y, and I take this y again here, connect this y here, and I take z. So, here I am available, either I am getting the complements of the variables and the variables themselves. Z and z prime are both available to me. So, I can connect z prime here, and I take this AND output and put it at the input of other input of this OR gate. Therefore, I am getting this function. Now, I can similarly do this and then again connect the output of this OR gate to this OR gate. So, I can similarly have z coming here, z is coming here, x prime coming here. I can take this AND gate, and this one can come to this OR gate, and this OR gate can be connected to this. Therefore, from here I am getting the function f. The point that I wanted to make here is, just by making these connections, I can connect the AND gates and OR gates at my will, and therefore, I can implement any particular Boolean function. All right. That serves the basis of the idea of all programmable logic devices. In the next class, I will discuss about how we actually do the interconnection, the basis of that, and we will deal more on FPGAs in next class.